All right. Good morning or good afternoon. This is Celso Battaglia. Let's see what's going on in our course. I have one student in the chat. Today is January 9, and we are in Planetary Motion, Chapter 3. So what's going on and what is closing today, discussion number 2 is Earth a sphere, and you have to provide, if you are watching this now, you haven't started the discussion yet, you have to provide some tests or evidence or data that support the claim that Earth is round or is to a very close approximation is a sphere. If you go to our book on chapter 2, there is a whole session on it. And again, the book is OpenStax, and I have this slide, some of the slides available here, but you should be able to download the entire version of your book. There are some flashcards that you can use as far as simulation is concerned. You can use simulation to test the laws of Kepler's, which I will be talking about in a second. There is homework that is due tomorrow, in fact, that is about chapter 3 homework. And I will talk a little bit about retrograde motion, what that means. And I think I mentioned before, I think a couple of days ago, but I will show you with some animation what exactly that is. And there are some extra credits to do, but basically the main point that to do is the discussion that is done on Wednesday and homework that is going to be closed tomorrow. So those two things you should try to get it done. And again, discussions I will not open. Once they close, they close. And they are about 10% of your course grade. And homework I will open in the last week of class. I will have all the homeworks available, and then you can redo them and try to improve grades. But not the discussion and not the extra credit. I also would like to call your attention for the extra credit. The extra credit will be scaled. All the points that you make will be scaled up to a maximum of 15%. So let's say there is a student that do all the extra credits and do them all right, which is difficult. So that student have an addition to his or her overall course grade 15%, right? So it's a lot of points, but it's very hard to get that. But right now your grade does not include extra credit because we don't know how to add that to the Canvas grade sheet. So keep track of your extra credit points. This is available. In Canvas, and those extra credits I will add. And first of all, I will scale that to up to 15%, and then I will add that to your overall course grade that is given in Canvas. And what I usually do, once I have that calculated outside Canvas, I upload a column with your course grade, right? And then I just leave it there for your inspection. I do not export my personal grade sheet. And then I put the grades on my web, and you're good to go. Let me briefly check and see if I have any question. I think I do. Okay, so no more questions. Start sharing screen again. Okay, what I would like to show is the main topics of chapter 3. The main chapter of topics of chapter 3 are pretty much Newton's law of motion. That's where everything ends it. But there is a historical background that led to Newton's law of motion and Newton's universal gravitational law, which is an equation that explains why materials get attracted and form systems like stars, like galaxies, like planets, so on, so on, so on. So historically, we saw there was this two worldview, the geocentric worldview, and later on the geocentric, the Earth-centered worldview was replaced by Copernicus' heliocentric worldview. But Copernicus' model was the sun in the center and the planets going around the sun in circular orbits, like perfect circles. And if that is true, if planets go around the sun in circles, the planets should go with constant speed. This is an outcome of application of mathematical laws to a body that happened to be moving in a circle around a fixed center. Now, this was not matching observations, at least had a lot of discrepancy. And what Copernicus did was, or those that follow Copernicus did, was to add epicycles in the same manner as it was done previously in Ptolemaic worldview. So Ptolemaic planets would go. Let me see if I can add that explanation here. We saw if you place Earth in the center of solar system, and then all planets would go around Earth in these so-called epicycles, right? Where the center of the planet orbit would be the one going in a circular way around Earth, right? And this big circle had a name. The name is deferent. And we saw this in previous chapter 2. Now, to match observations, what Ptolemy did was to place, first of all, Earth was in the center, but not exactly in the center, was a little bit off. And he fudged the model in such a way that the matching of planetary position with observations was very good, right? Now, this is Ptolemy worldview, Ptolemy. But in the Copernicus worldview, sun was in the center, and the planets also would go around the sun in a circular orbit, but the precision was not good. And then they had to introduce also this notion of epicycles, right? But even with epicycles, what the planet position, the prediction of planet position into the future was not being met by observations. So there was a problem with the model. So the history shows that Tycho Brahe, and he is a picture of it. So Tycho Brahe, he was one of the most skillful observers of all time. Perhaps Hubble was also one of those with strong skills in doing observations. In Hubble, you know a little bit more because there is a satellite that has on board a telescope that has taken fantastic pictures of sky objects, the Hubble telescope. So Hubble was also a skillful observer, but probably Tycho Brahe had the advantage of being one in the 1600, not with the knowledge and technology we have nowadays. But Tycho Brahe was able to come up with precise positions of planets in the sky. And then he had his own worldview, which was not a geocentric or not a heliocentric, was a combination of those two models. I'm not going to go in detail now, neither our book go. But the main problem is not a problem, in fact, he hired Kepler, it's right here, Kepler. He hired Kepler to be his mathematician and to try to find um, orbits using mathematical tools to find orbits and try to present his models through the language of mathematics. So Tycho Brahe had passed away. He died. He got an infection, and then he died. And Kepler inherited his data, his information, especially data on Mars. So Kepler then he worked hard to come up with three empirical laws of motion, of planetary motion. And in this figure here, 3.3, it shows in a way, if you have a cone, imagine this is a cone like the cone that goes in the hat of of child or kids in birthdays or clowns, coney head. So if you take a cone, if you cut the cone with a knife that happened to go perpendicular to this line, that's the line that goes through the center of the cone, is the line that has to do the distance from the line to the edges of the cone is the same all over. So if you happen to cut this cone with a knife that runs perpendicular to the line, you define a circle. Okay. Now, if you cut with an angle like in here, but you manage to hit the other edge. So if you start cutting from here, right? And then and then you go all the way down and you hit the other edge, you define a curve that is called ellipse. But if you cut with an angle that is too open, and in fact that is happen to be in this case here is pretty much parallel to the edges, what happened is you're never going to find the other side. So this is called a parabola. And if the line now is not parallel, but the angle is even larger, you have another curve that's called hyperbole. Okay. So Kepler knew about these figures, and the history goes that quite by chance, after several trial and error, he tried to see if an ellipse would nicely match the orbit of planets around the sun. And what he found was they do match. So the orbits of planets around the sun are not circles. They are not epicycles either, but they are ellipses. And ellipses are defined by what's called the semi or the major axis and the semi-major axis, half of it, and the minor axis and the semi-minor axis, half of it. And the way you build an ellipse with the strings and a pencil and thumbtack, like as you can see here, you take a string and you make a circle, right? And you tie the knot and you make a circle with the string like this. And then what you do, you take two thumbtacks and you stick those against a flat surface, and then with a pencil you stretch the strings, and then you just go around and then you make an ellipse. Now, the ellipse can be elongated if the size of the major x is much bigger than the size of the minor x, or in a special case of ellipses, if the two axes have the same size. Again, if the two axes, the minor axis and the major axis, they have the same size, we are talking about a circle. So a circle is a special case of an ellipse in which, in that case, the eccentricity, as we say, is zero. There is no eccentricity, so it's not flattened at all. So what Kepler found was, well, I can explain the planetary motion around the sun if the planets go around the sun not in circles but in ellipses, and if the sun happened to be located in one of these thumbtacks. I mean, there is not thumbtack, attaching the sun to the space, but and that point has a technical name, focus. So a foci, two foci are the two special places where we stick the thumbtack if we were to. So the first law of motion, the first Kepler law of motion, is that planets go around the sun, describing ellipses. Now, as a result of this, and now, in fact, Newton came in the 1700s, and he developed calculus in order to explain mathematically the motion of these planets around the sun. It was found by application of mathematical law in Newton's gravitational law. The second law of motion that Kepler had found before even Newton developed the entire calculation was that when planets are closer to the sun, they go faster than they go when they are further out. So planets, let's say if you place the sun right here, so this is a position in the planet's orbit that's further out from the sun than it is when the planet's here. So when the planet is closer to the sun, the speed in which the planet orbits the sun is bigger, it's larger than it is when it's further out. So that is Kepler's second law of motion, because in addition he found if you draw a line connecting the planets to the sun, and let me draw in a different place. So let's draw an ellipse. Let's draw the semi-major axis right here with the center. Here is the focal point. That's where the sun should be. Do a little star to represent the sun. And let's place a planet somewhere here. So planet's position is position A. So draw a line from A to the sun, and then to a position B when the planet's gonna be sometime in the future. So let's say that you manage to calculate the area swept out by the line connecting the planet at point A to the sun all the way to when the planet hits the point B. So the line connecting planets to the sun swept out some area, right? Like, what's the notion of area? Is the space in the plane occupied or swept out by this area? Let's say in a pizza, when you cut the pizza in a sector, and if you have certain amount of pepperonis in there, so a slice that is bigger is a slice that has more pepperoni, right? If the pepperonis are placed in a spaced way. So the area indicates the content, the surface content that is arise when that line is swept out the sector. Now, what Kepler found is, well, if you have another position of the planet, let's say position C, if you manage to find the same area, which means the same amount of pepperoni, There is no pepperoni, right? But see, this area over here, let's assume that is the same as the area covered by the line sun to point A, sun to point B. So the area sun to point C, sun to point D, right here, D, if the area happened to be the same, what Kepler found was, well, the planet will take a time going from A to B, time A to B, let's say 3 weeks, right? 3 weeks. So the time the planet takes should be the same as the time it goes from point C to point D, time CD. Now, if you look at my drawing, the arc CD is less than the arc AB. If the time is the same, it means that the planet has to go faster from A to B than it is in C to D because the arc is less in C to D. So you have to cover less miles, if you will, in the same time, so the planet has to take longer. So Kepler, because he had this valuable data provided by, not provided, I mean, the guy died, right? Tycho died, but he had this data he inherited from Tycho Brahe. So Kepler was able to find this law, which became and now is known as second law of Kepler. So planets sweep out equal areas in the space in equal amount of time. And one of the consequences is when the planet is closer to the sun, it goes faster than it goes when it's further out. The third law of Kepler is a mathematical law, and it was kind of motivated by philosophy, basically. I mean, Kepler's believed that the solar system was, as the planets would go around the sun, it would create a symphony, an accord of sounds that was associated with this notion of um, uh, um, the perfect pitch, the perfect sound, like an orchestra. So each planet would go around the sun and would take some time, and the distance of planets to the sun would create some sort of a sound because the distance is related to the size of a string. If the string is bigger, the frequency is somewhat higher than it is if the string is lower. If you play guitar, you know what I'm talking about. And then Kepler tried to find ways to relate the distance or the average distance of planets to the sun to the time it would take to complete a turn. And then he tried several formulations, and one of them worked, and that is the time. If you take the time the planet takes to go around the sun, period square in sidereal years. So if you convert that to Earth years, the period square, the time, the sidereal time square is equal to the semi-major axis, which means A, see this letter A right here, A to the third power. It worked. In fact, later on, Newton was able to prove this third law of Kepler with his universal gravitational law, and there is a factor that depends on the masses, not only of masses of the sun, but also the planetary mass. This is the second law of Kepler. So if area B is equal to area A, the time it takes to go from 1 to 2 is the same time t that takes the planet to go from point 3 to point 4. And then Newton came later with his nice equation. The force attracting masses is proportional to the product m times m, the product of the masses divided by the square of the distance is square. And g is a constant is a very small number, 6.67 10 to minus 11. It is a very small number, which means if you are watching or if you are hearing this lecture, and if you look around you, you have masses around you. You have a computer, you have a chair maybe, you might have a wall, you might have a house. So all of these features contain or have masses. So a certain amount of kilograms, certain amount of tons. If you have a car next to you, so a car is a few tons, few thousands of kilograms right there. So which means you have mass too. A human being like me or like you watching this, we have, let's say, rounding up, we have about 100 kilograms mass. So when you take your mass and you multiply by the mass of a car, which is a tons, so it's a big number, but the distance is 1 meter, 2 meters, 10 meters is not a lot, but this number over here, g, is very small, right? Which means the attractive force between you and your car it's not meaningful. You don't feel that attraction. We only feel the attraction of our bodies to a major, massive object, and that is the entire planet Earth. And that is one of the reasons we are unable to, by jumping, to get off and go out in orbit. Imagine if that happened. You give a little jump and you are in orbit. That doesn't happen, right? So if you jump up, Earth gravity force brings us down back to the floor because this factor here, mass of Earth, is a big number that overcomes this very small number over here, and then this attractive force becomes significant, and then we don't leave the floor. If you like to watch science fiction movies, especially there is a science fiction movie now, Passengers. So if you watch that movie, these people, they happen to be inside a spaceship that rotates, and that rotation creates a fake gravity force and keeps them kind of attracted towards the walls as if that is where a gravity, but it's not a gravity force. It's just centripetal force. In the reference frame of those people becomes centrifugal, kind of a fake centrifugal force, and gives the impression of them being squished against the floor. Now, where gravity comes by everywhere. I mean, gravity is the force that is responsible for bringing a solar system or stars into formation. In our galaxy, there are gas and dust spread all over the place, and the gravity force, if the gas itself met certain conditions of density, of consistency, so gravity will efficiently initiate a process of contraction, slow contraction, and over 10, 20 million years, this contraction will result into the formation of a star in a planetary system. There are other laws involved in the process of star formation. One of them is angular momentum, which was shown in the previous figure here. Angular momentum, see the ballerina effect, as these giant molecular clouds that are birth sites of stars. They have some small rotation, and when they fragment themselves and form in small clumps that will give rise to stars, as the size of these clumps reduce because this gas itself is contracting under gravity force, then they rotate faster, sort of a ballerina effect. And because of this faster rotation, the central or equatorial part of this cloud flattens and creates a circular or circumstellar disk where planets and asteroids and comets and satellites will be formed. So we are pretty much here in a planet Earth because of angular momentum, basically, and gravity. I mean, these two forces. Okay. So this is chapter 3. Chapter 3 doesn't have a lot of further information besides the three laws of Kepler and Newton's law of gravity. And it's very important because it introduced this notion of universal gravity law and these laws of motion, of planetary motions, are so precise and so important that all the space program is based on that. I mean, we know how to send, when I say we, is people at NASA and ESA working on, on, on launching rocks and sending probes out to several places in the solar system. They use the Newton's law and its precision to achieve their goals. So it's not just an absurd theory that somebody woke up and say, "Hey, that's what I think it is." No, it has been met with observations, with checking and balances and all of that. Okay. So let me go back to the chat room. I have to find my icon. There you go. So, do you have any question? Do I have any question, Alexandra?
No question.
All right, very good, very good. So, let me stop taping so I can talk to you.